Good, Naresh. You're Indian also.
That doesn't mean anything. So screen two.
No, don't do that.
Let's take screen two, right?
Actually, yeah, that makes sense.
Okay. And I hope the audio is right.
Oh, sorry. It should be right.
Jean is chair for that session. And take care of any information.
Just a second. Let's just hold this. No, I'm not. I'm just checking the Zoom.
Can we check the audio?
Yeah, that's what I'm saying.
Yes, here itself.
Okay.
It's correct. This is correct. And then recording is on. Just share and we're good to go. You forgot to turn on screen share.
Yeah, I know. Yeah, but I can't turn it on without.
It was fine, just.
Oh, really know.
Yeah, just share screen two and.
Don't see screen two.
Mini screen will be okay, bottom of it.
Yeah, that works.
It's fine, it's fine.
Or you can use the mouse for a laser pointer.
Okay. And your mic.
And your mic should work.
Okay, so then I just show here. Okay, it shows up there. Okay.
Yes.
One small thing I need to do. Okay.
Yeah, I could just minimize it also.
Yeah. Can I please do one small thing?
What do you want to do?
High floating meetings.
What is video
Goes the other thing.
Now we have the whole thing.
Yes, yeah, still 5 minutes left.
We are ready to. Thank you. So how do we make us? You can just turn it on.
Yeah,
This is from the back, right? Yeah.
yeah, just make it sit on your ear. It should be good.
Okay. I want to just log this. Okay. Hello. Thank you. Maybe we can talk after this session. Can I start in 1 minute? Nobody left. Okay. Very good.
Okay, ladies and gentlemen, good afternoon. Now we start this section, and this invited talk will be given by Professor Prasianakis, and the title is Accelerating Numerical Simulations from Microfluidics to Geological Perspective. Yes, please.
Okay, thank you very much for the introduction. So I'm actually a doctor, not professor, but this is a minor detail. So then this presentation is relevant to how we can accelerate numerical simulations to solve some practical issues. Most of the modeling is relevant to lattice-Boltzmann, of course, the underlying models. And with that respect, I have to mention that I did my PhD with Ilya at the year of 2005 to 2008, where we developed some models, lattice-Boltzmann models, which we have derived some yet another equilibrium. Plus, we have added some correction terms such that to guarantee that the lattice-Boltzmann scheme we had can recover the Navier-Stokes equations. These kind of models are used in the background. I will not go into the details of these models. And then this work that I will show, it's a collaborative work with several people. 3 of these people will also have some presentations in the next days. So the motivation behind this work, then the slides are not changing, so maybe, sorry for this. Okay, I found the magic key. So I will first discuss a bit about the motivation behind this work. Then I will discuss what kind of technologies we need to achieve our goals. And this goes through lab-on-a-chip devices and digital twins. And then the simulations we are conducting are too slow to apply in practical problems. And then we have to find ways to accelerate. And then I will discuss a little bit how we accelerate geochemical calculations, and then some uses of machine learning for upscaling and sensitivity analysis. So in Switzerland, 30% of the energy, the electrical energy is produced by nuclear power. 60% is hydropower and 10% is renewable energies. So this means that we have nuclear waste. So nuclear waste is currently stored at the Paul Scherrer Institute, the institute where I'm working. This is a temporary storage, but in the long term, we have to store this nuclear waste underground safely for the next 100,000 to 1 million years. So this is, of course, very challenging. Because we don't need only to bury them underground, we have to guarantee that the radionuclides, they will not escape to the biosphere. So at the moment, all countries have agreed that they store their nuclear waste locally. So Switzerland has to store locally. And up there you see a map where there is the potential location. So the potential location has been identified. A license application will be submitted next year. And then if everything goes well, at around 2030, there should be some referendum if the people of Switzerland, they like this solution or not. Therefore, we have to address in a very scientific way all the challenges that appear. What you see here is the low-level waste, and the high-level waste of the nuclear fuel is the high-level waste. In the nuclear waste repository, there will be several coupled processes occurring in the next hundreds and thousands of years. And then we have to take into account all these kind of processes. And as you understand, this is really science fiction. We cannot really model all the microprocesses and all these coupled processes in a consistent way. Of course, there are model abstractions, and then we try always to improve the realism of these models. So I'm going to show is not only relevant to the nuclear waste management, it has to do with geochemical reactions in the underground, which applies in several kinds of problems. So, for example, we have the enhanced oil recovery, we have CO2 sequestration, we have geothermal, and we have all the geoenergy resources. So for that, this is maybe the vision. We want to have a digital twin. So what is the digital twin? A lot of things are said nowadays about the digital twin. In our definition, it's a modeling-based tool of increased realism, which can really describe the real process that take place in the physical counterpart. So for the cases that we're considering, even from the simple laboratory experiments to the full nuclear waste repository processes, we need to have some specific qualities. So we have to have high fidelity simulations, so very good numerical models. We have to have multi-scale description, we have to have multi-physics, and we need ultra-fast simulations. So just coupling a molecular dynamics solver with a macroscopic solver will not work. So this brings us to the challenges behind this work, and then we have to find ways to bridge heterogeneous codes which describe processes at different scales. And then we have to accelerate all these numerical calculations without losing accuracy if possible. Regarding the experiments, we hope to augment the experimental observations by creating these digital twins. Just some examples of modeled processes you see up there. There is, when we make the tunnels for the nuclear waste repository, we bring cement and clay. This is the clay material 400 meters below the surface of the ground in Switzerland. We bring them in contact. And then because of the geochemical contrast between the cement and the clay, there are going to be some reactions which they will result in degradation of cementitious materials, and then it will change the properties, the local properties of permeability and diffusivity. So it is important to know how these geometries evolve, and then we can try to apply predictive models. Another topic is here you see a high-level waste, so from the nuclear fuel. When the radionuclides will go out and they will escape, there are some mechanisms that they will retain. So one mechanism is the sorption on the clay material. Another mechanism is the co-precipitation of barium, radium, strontium sulfate. So how to address these topics? We start from the small scales, and then we try to design some chips, some very small devices where they can allow us to study all these geochemical reactions very fast and at small scale. Here you see the Mohammed, so he defended his PhD in January, but he had really nice time in suggesting and designing this kind of chips. So here what you see is a microfluidic chip where we have some reactants and then we produce some crystals. And we want to know how the crystals are reacting, how fast and under which conditions. Then just to appreciate how small this is the whole reactor itself is maybe 70 micrometers, which is smaller than the human hair. And then, of course, this poses another new number of challenges of how to design these experiments and how to interpret these experiments. So advantages of very small lab-on-a-chip type reactors is that we have a miniature environment, we have very short time scales and small quantities of reactants in comparison to a larger laboratory experiment, which is of the order of 1 meter or half a meter and will take weeks to observe some reactions ongoing. Then the challenges, of course, are the in situ conditions, how to monitor what is happening. And especially when we have chemical reactions, the situation becomes more complicated. And of course, we would like to control also experiments. And then it will be always nice to be able to predictively, a priori, design the experiments such that we capture the physics we like to have. So in the example that I will use here as a base case, we have two streams. So within this microfluidic chip, we inject two fluids. One contains strontium chloride, the other sodium sulfate. Then these two, they meet, they precipitate, and they produce some crystals. So this crystal is a Celestine crystal. And you can see what happens in this video. When we run the experiment, we see the crystals growing, and this is all about it. What, as experimentalists, we would like to, of course, know is what is the flow rate there, because this is a microfluidic cell. What is the chemical composition at the interface that grows? These are the crucial information that define the reaction rates and the physics of the problem. So this we cannot get from the camera. There could be some techniques, but they are very difficult to really know what is the speciation and the exact flow field during the experiment. So what we have done, we have resolved the flow field when there is no crystal. Then you can see these streamlines. This we have validated by injecting also some glass beads, so we know that our models, they are correct. And then, of course, during the evolution of the experiment, we can resolve what is the updated flow field. Then, at the same time, by having the chemistry on top of the fluid solver, we can know what is the chemical composition of the fluid at every specific location. This is, of course, the model prediction, and we have to see how close we are to the reality. Then what we can do on top of that is that when the crystals grow, we can just predict by the reaction rates we have what will be the growth rate of the surface, and then compare with experiments. If there is some substance that we don't know what is the reaction rate, we can measure it like that. So for example, here it will be interesting to see interaction with different metals. Now, all these things are good, but in reality, there have been the experiments. After several months of experiments, we isolated some experiments, then we received the data to make the modeling. The modeling took, of course, some time, and then the simulations, they took also a lot of time, and then a fully coupled advective, diffusive, reactive lattice-Boltzmann solver, which is used here, really took a lot of time to resolve the flow. We could only resolve it differentially when we have the crystal for the next milliseconds what will happen, but we could not afford to solve for the duration of the experiment, which was several hours. So this was really a limitation, and we had to find ways on how to accelerate our simulations. So the first step we took, which certainly were not the first, and of course we will not be the last ones. There is already some papers already 30 years ago that neural networks were used as surrogate models for the chemical solver. So combustion was more in fashion back then, and then since 2016 in the geochemical research, there is a lot of people trying to apply surrogate models, data-driven models, and surrogate models. So the idea here is that we have the mass transport solver, which is the lattice-Boltzmann one. This is very fast compared to the thermodynamic solver. The thermodynamic solver has to solve also a number of equations in an iterative way at every grid cell, at every time step. So then apparently, when we checked it, it was occupying 99.9% of the calculation time, which means if we have to accelerate something, we really have to squeeze there. So then we just replace with a surrogate model. What this means is if you have a chemical composition, here we have three components as an input, then the result of the equilibration or the speciation will be to know how many ions we have, what is the pH, what are the precipitates, for example, how much calcite we have, how much dolomite. And then this is the input, this is the output of the model. And then here you see some kind of manifold plotted how the neural network captures the data. Then why we do that? It's because the geochemical solver can provide on the same CPU core, on the same computational system, only 300 equilibrations per second. This is the limit of the geochemical solver, while the neural network can go at a rate of 3 million per second. So we really have a speed up of that part of the code of around 10,000 times, which is enough if the accuracy is also acceptable. So then the game is if we can produce this kind of objects to run in parallel with our code. So then we have done a test. Then what you see here is the evolution of this experiment. What you see as different colors is the evolution of the concentrations during the experiment. And then there is the typical workflow where one uses the geochemical solver. And there is another workflow where we can use a lookup table or a neural network or some other kind of surrogate model. Then when we put everything together, we then have produced this kind of plot where what is to be seen here is that there is some evolution of some property. What is to be seen and appreciated is that in this case, the neural network was trained so close to the physical solver or the geochemical solver that it produced identical results. So these curves, which show they have some characteristic quantity of the experiment, they almost overlap. If we zoom in here, still we cannot distinguish the neural network solution from the fully coupled. What we see down here is the lookup table approach, linear interpolation in a lookup table. Now, this is, of course, a proof of concept, which says, okay, maybe we can try to go in this direction. And this, of course, pays off when higher dimensionality problems are considered. Another step we had to go through is we had to change a little bit our algorithm and make an adaptive time stepping. So apparently our system passes through some transient states, which when the code identifies, it can increase the time step. And then, of course, the simulation goes faster until it reaches another point where it has to go again with a very fine time discretization. By doing this, it was possible to reproduce the experiments. Sorry, this video is not playing actually, but then what you will see will be that the crystal is growing. And at the end, with this adaptive time stepping, we can compare here now what is the predictions of our models and what is the reality, what happened. So the green area is the model matches the experiment. The red is the model, there is some over prediction. And yellow up here a little bit, there is some under prediction. There are a lot of uncertainties of why this could be happening. We are very happy with this result, especially when we see that when we combine the adaptive multi-stepping plus the geochemistry using a surrogate model, we have a solution which is 10 to the power 5 times faster. So essentially, this allows to have a real-time companion of the experiment and opens the doors to do, at the time of the experiment, some sensitivity analysis and to many, many different avenues. To close the loop, we need to, of course, have a system which has a look to the experiment and gives a feedback to the model. And this is what we are currently working at. What you will see here is in this microchip, there is the identification of the region of interest. So when a crystal is detected, we know where is the location, then we can tune the model and then maybe pass the information. And then on the right, what you see is the measurement of the reactive surface area of the experiment. So just to summarize maybe about these possible ways to accelerate simulations, there is the neural network for the chemistry. Then we have the adaptive time step, and then we also have Swiss supercomputing. So in the Swiss supercomputing center, we have a big array of GPU nodes, which is currently updated actually, and it will be in the top 10 of the world very soon. We're still running in the old machine. And then we have an in-house GPU code, which was developed at PSI the last 10 years. And maybe just for a comparison, the chemistry can go in a CPU, maybe let's put it that way, at around 1,000 updates per second. On the same CPU, a typical lattice Boltzmann will go with 1 million updates per second. I'm sure there are solvers that go much faster, maybe 10 million. And then the chemistry, yes, and then the chemistry in the neural network is also at this order. So we can reach 1 million per second. So this means that is not anymore the bottleneck, the chemistry. Then when we want to have a pure GPU application, then there is currently no chemical solver which can be run purely on the GPU. And then the GPU provides another update at around 100 times. And running the neural network on the GPU is very straightforward once we have it, or any other surrogate model. running the geochemical code on the GPU requires to rewrite the whole code. And the authors of these codes, they are not willing to spend their time to translate their codes to CUDA, for example. So with that said, I'm currently leading a geochemistry and machine learning benchmark within the URAD joint initiative. Several groups around Europe who are interested, of course, in this kind of simulations. They joined forces, and then we have tested many different models, machine learning models in very complex, let's call it complex geochemical setups. And the results are looking very promising. So here we compare some of these methods. So with that said, it's time to go maybe to the next topic that I would like to address, and this is relevant to upscaling. So here what you see is a porous medium. Maybe this is relevant to oil exploration or calcite acidification in the underground for geothermal flows. What we have here is geometry. So this is created through Voronoi maps and some kind of statistics. And what you see in this graph is the permeability versus the porosity. So we do have some acid coming in and dissolving the porous medium. And then this changes the porosity and the permeability. So typically we have this Kozeny-Karman type of equations where we can use to upscale results. So maybe some empirical correlations are used. However, when we look at the details, it is clear that the flow has an effect on how the dissolution proceeds. So what you see on the top simulation is in a high Peclet, high Damkohler case. So maybe higher acidic concentration, and this creates some wormholes. So these are called wormholes because it penetrates. In another case where conditions are a bit more mild or velocities are different, we have this phase dissolution. So in the oil industry, of course, we're interested to open up with wormholes the porosity, and it's interesting to know where we stand. Now, when we look maybe closer to these details, then we will see that these processes are extremely non-linear. So if we try to fit a correlation, then this will be porosity power 14 in some regime, or it could be porosity power 1. So then this clearly indicates that so the zoom out was maybe too much. Okay. So then this indicates that we have different regimes where we can not predict a priori what will be the effect on permeability. It really depends on the situation. Now, wanting to upscale these results, we resorted in the following concept that we have to encode all these physics that happen in this elementary pore scale geometry. And then we can pass the information. So what you saw as curves, we can pass this information to a macroscopic solver. So the lattice-Boltzmann discretization was 0.1 micrometers, while the macroscopic code had a discretization of 0.1 meters. Then we uploaded, we connected these codes. Obviously, it's not an option to solve one lattice-Boltzmann simulation for one time step of the macroscopic solver at every grid point of the macroscopic solver. However, with this kind of physical abstraction and maybe this machine learning or support, we can afford it because this kind of objects, these neural networks are very fast in their predictions. They have some accuracy. Now, it's not everything perfect at the moment, but this is a very promising way. So then with that said, I jump in the next step, which is relevant to sensitivity analysis. So sometimes we have one simulation, for example, for an airfoil or for the geological repository. But in order to optimize, we need hundreds of these or thousands of these or maybe millions of these. So then, of course, it's not practical to make millions of these simulations since we barely can afford to make a few tens of these. So the idea here was that in the previous, we have seen that we can replace the thermodynamic solver. Now we say, okay, let's replace the full solver. We can try to train the neural network or another surrogate model using the output of the full reactive transport model, and then use this for exploring our optimum design or for our sensitivity analysis. And let's see how far we can go. So in this example, we wanted to have the sensitivity analysis of nickel migration in clay. So nickel is a proxy for other radionuclides, and there are experiments, there are several benchmarks. And then we wanted to see how to accelerate. So what we're interested to do some global sensitivity analysis, because then we can capture the nonlinearities and the interactions between the input parameters. So changing one parameter at a time when we have 27 or 30 parameters is also a sensitivity analysis, but the global sensitivity analysis reveals more connections. And then we have to do a lot of simulations. So it seems that 30,000 of these simulations are the bare minimum to explore a 5-parameter space using the Sobol analysis. So this is a sensitivity analysis. And then we have started with a larger system, which we had 17 species and 58 complexes, and then we have reduced the species. We ended up to 6 parameters. And then the typical way to do this analysis is we have our physical simulator, we have to do 30,000 simulations, and then we get our sensitivity analysis. Now, the alternative way is to try to train with a minimal set of these physical simulator results, to train with a minimal set our meta model, which in our case was again some neural network. And then if this is trained sufficiently with 100 simulations, we hope we can do the rest of the Sobol analysis, the rest of the 29,900 simulations using that object. So this apparently works. And then maybe here I just show you the system. So this is the system of the reactions we were investigating. This is maybe the high-level waste, and then we have a simple problem in terms of space, but very complex in terms of chemistry and conditions, where we have a domain, and then nickel diffuses, and then we test how much nickel is where after how many years. Then these are called breakthrough curves, what you see here, and then these curves, they are plotted 32,000 such curves. Each one of them, we change one of the parameters of the system, and then we get this cloud of behavior. Now, what we did, we trained in a subsample of this, maybe only 100, and then we run the Sobol analysis. So the Sobol analysis cannot run with 100 species, with 100 samples. It needs really 30,000 or even more. And what we get is that we get very similar quality sensitivity analysis results. Here, what we have done, we have trained the model to be able to reproduce these breakthrough curves. So we don't, this is the only information we wanted to have from the simulation. And then what you see here as bars is the Sobol index. Then high bar means that this parameter is more important than the other parameters. This means that we can now focus our research in identifying these parameters better and constrain our models, or that we have to be careful with these parameters and their influence in the result. Then here we have a speed up of 2 to 3 orders of magnitude. And this is, of course, an envelope to the previous ones, right? I mean, this is adding another layer of acceleration if we are interested in inverse modeling, in optimization, or in model parameterization. So with that, I will just give very shortly 2 or 3 examples of where we apply also some digital twin concepts and some machine learning, this time without the lattice Boltzmann, but it's not excluding the lattice Boltzmann. So for the nuclear waste management, it's important, for example, to make some demonstration of what will happen when we emplace the nuclear waste. So the nuclear waste will be hot for a few years, and then we're interested to know what is the thermal pulse of this waste canister. There have been some experiments in the underground Monterey laboratory where the people, they actually have put some canisters which do not contain, of course, radioactive material, but they are heated constantly the last 10, 12 years. And then they have monitored with different sensors all the thermal pulses and the humidity. Then what we have done in this case, this is work mainly of a postdoc, Guang Hu. And then this we have put in a model all the details, including the heterogeneities of the bentonite. So the bentonite is the material that's filling up these canisters. All small details are included, and then we try to reproduce and see if we can really get the signals, the temperature signals and the humidity signals. So in this case, we have used a hybrid kind of approach. We have gotten the sensor data for humidity, and we have created a surrogate model, and we have somehow coupled this with a physical solver which solves the heat equation. This way, we have managed to exactly capture all the thermal behavior in this underground experiment. And this gives us confidence and a way to couple with real-time sensors, our physical models. Then, last but not least, we need to input in our models the geology of the Switzerland. So NAGRA has conducted some geological survey in Switzerland, and then we have access to the boreholes. And the boreholes are some cores of stones or of rocks, which are analyzed. Now, in our models, we need to have a resolution of a few centimeters, or we need to really resolve to very fine scales. However, not always we have data available of the mineralogy or of the diffusivity of this kind of rocks. So what we did, we implemented some computer vision and machine learning to first to classify the rocks. So these are the kind of cores that we have. And then we classify first to know from where this lithological, to which lithological unit it belongs. This is, let's call it a simple exercise. We have this maybe 1 or 2 kilometers course, a column, and then we just train it, and then we try to classify. And then we were not interested, of course, to classify because this is already done, though in some applications it's also very interesting. We were interested to do the regression. So we get a picture, and then we just need to know what is the mineral content. In our case, we wanted to know how much carbonate, how much dry clay, how much silicate we have. And then what we did, we created some specific model using all these nice tools that exist around. And then we have reached some lithological classification. This is almost 96% accuracy. So we throw a small slice of the rock, and then we ask the model to tell us in which lithological unit it is. And then, moreover, we also have the regression, which means that it gives us also a prediction of what is the content, what is the clay, carbonate, and silicate. In our next step, we also want to include diffusivity, so we are in the process. So hopefully we can get the full column with local diffusion coefficients, which will be the input for our numerical models to simulate the transport of radionuclides from the canister to the biosphere. So this brings me to the summary of the talk. So I have shown to you, and we will see also in the next presentations, maybe in some of the sessions in this conference, that machine learning is a key enabling technology for accelerating numerical simulations and for bridging the scales and physics. Then we need efficient algorithms and high performance computing. And this allows to go in the direction of design optimization and to conduct also sensitivity and uncertainty analysis. This digital twin, it's a major issue at the moment. There are many efforts to try to produce these kinds of digital twins, and then I think the community is slowly converging to some model realism that can be called digital twin. More details on specific topics you can find in the talks that will follow. So there is Athanasios, so he will present his research relevant to boiling and in a nuclear reactor setup through a porous medium. Then there some numerical models, of course, are used, lattice Boltzmann, and then there is a coupling to molecular dynamics and use of high performance computing and GPU computing. So then there is another two talks. Then one is relevant to cement clay interfaces and all these reactions, how they change the clay and the cement. And actually the adaptive time stepping algorithm will be presented there. And then last but not least, there is the presentation of Haunan. This is relevant to another set of experiments and how to create the digital twins and how to complete the step of inverse modeling. So with that, we have to acknowledge the funding agencies, so NAGRA, SNF, Swiss Nuclear, EU, and of course the precious work of all the collaborators behind these slides. And I'm happy to have any questions.
For a very nice talk. Any questions or comments? Yeah, please.
So once upon a time, there was an idea that you could use separation of timescales between the reaction rates to extract a level of the model, and that was sort of informed by looking at the structure of the model and reaction rates and separation of time. I think you used to do this before we got into doing lattice Boltzmann. So I find it a bit sad that then actually just throwing all that away and saying treating it as a black box seems to work better.
So this, you mean the neural network is a black box? So any kind of polynomial of ninth order, I'm not sure if one can really grasp what it is. So, but this is maybe a black box, but it has specific properties which we can measure. So we know how to train these black boxes, and we know how to make them more accurate. And as soon as these black boxes, for the same input, they provide the output that we are expecting, and this is in a very well-defined area, and they are not overfitting. So this is something that one can check. Then we can trust these black boxes. Now, it is maybe black box because if we have these neurons, we can write down the equations, but it will be very complicated to understand. If we have 10,000 neurons, it will be complicated. If we have 2 or 10, then it's a simple set of equations. And then, of course, the weights of these equations, we cannot possibly know what exactly they mean. But this is the same if we fit a polynomial, or maybe in this example, we can ask why this is porosity power 13. What does this mean? It's a nice fit, but what is it of that? Why? Or what is the coefficient in front of that? So then, of course, the neural network has millions of this and hundreds of this. And things get complicated when we have this image recognition. And there, there is some tricks and where one can apply, where it should not apply.
Yeah, please. I had a question about there was in the beginning a section where you had crystallization and crystal growth. So is the crystal growth actually coupled to the species field, and is there like actual growth of the crystal?
Yes, exactly. It is.
That controls the evolution of the solid phase.
So the solid phase is just the solid of the lattice Boltzmann, and then we have the specific reactions, and then when we dissolve, this disappears. When we precipitate, we have a nucleation. We have applied the classical nucleation theory, and then we know how much precipitates is appearing where, both for homogeneous and heterogeneous nucleation.
Practice, can also this be replaced with like an Allen consolver to follow the solid phase? that's growing. So in practice, people usually use for, especially for anisotropic crystals, they couple Ln con to the flow field of the species.
Yeah, so in this case, Mohammed, so he had also taken into account how the orientation of the crystal growth. And this he did with equations the old traditional way. So he didn't couple with some other code. So these crystals, when they grow, they also have some preferred orientations. The regime I showed, it's more hydrodynamics controlled, this growth. Yeah.
I have one question.
Yes, yes.
That at the post scale, the reaction may lead to some fractures.
Yeah, yeah.
So in the Darcy model, I see that it just obtained a concept of one single permeability. Yeah, one single permeability. Can this one single permeability reflects the evolution of the fractures as the Darcy scale?
So what we have here is, depending on the conditions, we follow a different path. So then you see this from the curve here. So this is the permeability axis, and this is the porosity. And then this is the change of porosity because of the dissolution. So then the porous medium, the same porous medium, will have a different permeability depending on the acid that we inject, the flow rate of the acid, and yeah, the acidity.
Porosity is changed locally.
Yes, exactly. So what
Changed with chemical reaction. Yeah.
Yes, also the chemical reactions play a role, and then this is the Damkohler number plays a role. Yes, exactly. So this is a fully coupled problem, and this is the reason why we cannot have one empirical formula describing all these kind of nonlinearities.
If no other items, now close this invited talk. Thanks, Professor again.
Thank you very much.